Solving reinforcement learning problems using supervised learning has been seen quite hard because supervised learning uses error signals, whereas the agent receives evaluation signals in reinforcement learning settings. This problem becomes more challenging for robots because robotic tasks require complex, continuous, sensory motor trajectories, and mostly the robot receives a single reward from the environment for the whole trajectory. Moreover, in this environment, the rewards can be sparse. There may be local minima or multiple solutions. We propose reward-conditioned neural movement primitives or RCNMP for these challenges. RCNMP generates trajectories by conditioning them on rewards, uses variational inference to construct a stochastic latent space, benefits from evolutionary strategies by applying a novel, self-organized crossover operation in latent space and a mutation operation in task space. First, previously experienced sensory motor trajectories and their corresponding rewards are stored in the replay buffer. Then these trajectories are given to RCNMP to learn a reward-conditioned policy mapping function. By conditioning this network on Rmax, high-reward trajectories are generated. We temporally blend these trajectories by a novel crossover operation that is applied in the self-organized latent space to increase diversity of the population. Then, to further increase the diversity and encourage exploration, mutation operation is applied in the form of adding Gaussian noise in task space. We incorporate a PD controller in our model to ensure smooth movement and guarantee for reaching the goal. These trajectories are then given back to the replay buffer and the loop continues. Our framework continues to improve its samples and progressively finds better trajectories. We validate the stochastic sampling in latent space by comparing our method with its deterministic counterpart, CNMP. CNMP generates only the mean trajectory of the demonstration distribution, which goes through the middle since it is deterministic. However, our CNMP generates trajectories that cover the whole demonstrated range due to our latent representation stochastic sampling approach. In our second experiment, we show the stability of our approach over a policy gradient reinforcement learning algorithm on top of a CNMP architecture, ACNMP, and the importance of our crossover and mutation operations. Our algorithm offers a more stable learning in comparison with ACNMP. Crossover accelerates the learning at early steps, and mutation operation is needed for small adjustments. Adding more random points to the environment increases complexity and affects the performance. In this experiment, we want UR10 to carry a bottle from the start to the end position by crossing between the bottles on the table without touching them. The robot receives punishment as binary signals for contacting with each bottle and not crossing between the bottles, and a continuous signal for the length of the trajectory. We compared our method with two state-of-the-art methods. We observed that RCNMP requires less than 20% the number of samples for this task compared to these methods.